Hey everyone, hope you're doing well. Today is going to be all about drawing Lewis diagrams for elements in chemical compounds. The first kind of diagram you probably learned in chemistry is going to be the Bohr-Rutherford diagram. And it would look a little something like this. I'll create one for sodium just as an example. So the idea of a Bohr-Rutherford diagram is we are accurately representing all of the electrons associated with an element. So in sodium's case, we have 11. The first orbit has 2. The second orbit would have 8, and we would add those one at a time and also clockwise, which is what I'm doing here. And then finally, it has a lone electron in its valence shell. So that would be a Bohr-Rutherford diagram for sodium. Now, that took a little long, and when we're dealing with chemical reactions and chemical equations, it doesn't really matter how many electrons the element or atom has in total. What we really only care about are the valence electrons. So that's when Lewis diagrams are super useful, because if I wanted to write a Lewis diagram for sodium, that's literally all I would have to do, because I'm only representing the electrons in the atom's valence shell, which would be 1. And if we go down to our examples here, I'll show you a couple of different ones. Magnesium has 2 valence electrons, and usually we follow the same rules as with Bohr-Rutherford diagrams in terms of how we place our electrons. So we're going to be doing those one at a time clockwise. Looks something like that. So this would be accurate for magnesium since we have 2. Oxygen, I believe we have 6 valence electrons. So if I do the diagram for oxygen, we'd end up with that. Finally, carbon, we've got 4 valence electrons, and we'll add those one at a time, going clockwise. Okay. So making individual diagrams for elements is pretty straightforward, but what if we are dealing with a compound? So we have 2 atoms bonded together. In this first example, we have an ionic bond, and the way we're going to represent the ionic bond with Lewis diagrams is first by writing out the usual Lewis diagrams. So sodium would have 1, chlorine would have 7 valence electrons. So this would be accurate for the elements on their own, but we know that they're in an ionic bond. So sodium has given an electron to chlorine. So I can rewrite this showing the charges on my 2 ions. And what I'm showing on the electrons is that sodium has given 1 electron to chlorine. So I'm showing 0 electrons here, and then a full set of electrons for chlorine with that negative charge. You might see some diagrams like this, where none of the electrons are actually shown in the valence shell. And that's fair too. It's really a preference thing. I prefer to draw the electrons on my negative ion just to show that the positive ion has donated an electron. So that would be for ionic compounds or ionic bonds. What about covalent compounds? So we've got two chlorine atoms bonded together. And what I'll do is I'll just draw out two chlorine Lewis diagrams. And I'm actually going to break my rule of adding the electrons perfectly clockwise just to give you a better understanding of how these electrons are going to be shared between atoms. Each chlorine atom has 7 electrons in its valence shell, and they're both 1 electron away from becoming stable. So what's going to happen is this chlorine is going to share its electron over here, and this chlorine is going to share its electron over here. And the way we can represent that in using Lewis diagrams is just by a straight line that would connect our two elements. So if I were to rewrite this, it would look something like this. The line that I've drawn, this represents 2 electrons, but in terms of the individual atoms, it represents 1 electron being shared from here and 1 electron being shared from here. That's why if I counted all of the electrons on an individual atom, it will still make sense. Because here I have 6 dots plus 1 electron in my line for this first chlorine, and I have the same thing here, 6 electrons and then 1 electron being shared in the line for this chlorine. So that looks good. Let's move on to some more complicated covalent compounds, because there are a couple of rules that we need to follow when we're dealing with compounds that contain different elements. Rule number 1, just count your number of valence electrons. Let's use water as an example to run through all of our rules. So I'm just going to count how many valence electrons I have. Hydrogen always has 1 valence electron, and I have 2 atoms of hydrogen. They each have 1. That's a total of 2 valence electrons. 1 oxygen atom will give me 6 valence electrons. So if I add these two numbers together, I've got a total of 8. So that's rule number 1 covered. Rule number 2 is connect your elements together with a line, which will represent the shared electrons, and subtract 2 electrons from your valence total for each line drawn. Okay, now it's time to draw our diagrams. Do we have 2 hydrogen atoms and 1 oxygen? That tells me that oxygen is going to be our central atom, meaning that hydrogens are kind of bonded around oxygen. And I need to connect them with our lines. And now we need to subtract 2 electrons from the valence total for each line drawn, because as I mentioned before, each line represents 2 electrons. I have 2 of those. That gives me a total of 4. Now I'm left with 4. Rule number 3 says, add the remaining number of electrons to match the usual valence shell for each element. What do I mean by that? Well, let's take a look at hydrogen first. It started off with 1 electron, and it's attached to 1 line. So that looks good, because the 1 electron that hydrogen started with is being represented in this line as it's being shared with oxygen. So that's okay. What about oxygen itself? Oxygen started with 6 electrons, and it has 2 lines attached to it. So 2 of its original electrons are being represented by the lines, but we would still need to show 4 more electrons on oxygen. So let's do that. And now we've made sure that rule number 3 is being followed. So that looks good. Moving on to our second example, we have carbon tetrachloride. Let's count our valence electrons. One carbon will give me 4, and 4 chlorines should give me quite a few because they each have 7. So that's going to be 28 electrons. Add them up. I've got 32. Now, same deal here. I need to pick the central atom, and in this case it's going to be carbon with chlorine attached around it. Okay, and each line represents 2 electrons. I have 4 lines. I need to subtract 8 from my total. Now all that's left to do is add the remaining number of electrons where needed. Let's start with carbon this time. Carbon had 4 valence electrons, and it has 4 electrons being paired to other atoms. So carbon looks good. For chlorine, they started with 7, but they each only have 1 electron being a part of a line. So what I can do is I can add 6 electrons to each of my chlorines, and that should balance me out. Because each chlorine started with 7 electrons, we have 6 shown by the dots, and then 1 being represented in that shared pair with carbon. All good. We do have some trickier ones though. So what if things don't go according to plan? If we follow these rules, we might realize that we're getting stuck. And I'll show you what we can do when that happens. We are going to look at CO2, or carbon dioxide, first. Let's count the valence electrons. So I've got a total of 16. And then if I show their bonds together, I've got 2 lines, which represents 4 electrons. So now I've got 12 left to show on my diagram. And let's say, okay, I know oxygen is lacking some electrons, so let's just plot those over here. But something's not quite right, because oxygen started with 6 electrons, but now it's being represented with 7, because we have 6 dots here and 1 electron in our line, which means that overall we're showing a charge of -1. And for Lewis diagrams, we would say a formal charge. So we have a formal charge of -1 on our oxygen on both sides. And if we look at carbon, carbon started with 4 electrons, but it's only showing 1 electron here and 1 electron here, meaning that we're missing 2 electrons, thus giving it a charge of +2. So this is not entirely accurate, because yes, if we were to add up all these charges together, we would get a net charge of 0, and that would make sense because carbon dioxide does not have an overall net charge. But we want to make this as accurate as possible with regards to the electrons associated with each element. And the way I can do that is by adding extra bonds. So let me erase what was going on here with our electrons and try this again. Okay, so we have 12 electrons. We know that if we plot those on now, it's not going to work. But what if I were to add an extra bond between carbon and oxygen? Now, if I were to put some electrons on oxygen, let's see its formal charge. So we started with 6 electrons. We have 4 being represented by the dots and 2 in our line. Therefore, we are showing 6 electrons, and it now has a formal charge of 0, which is much better. And if I do the same thing on my other oxygen, that works as well. But we need to make sure we have the right number of electrons from our original number that we counted. So we had 12 when we were only using 2 lines, but what if we were using 4 lines? So now this 4 becomes an 8, and we're left with only 8 electrons to work with. Well, it just so happens that to make our oxygens work, we only need to put 4 electrons in each one, which is a total of 8. We can also check how carbon's doing. Carbon started with 4, and now we have 4 electrons shown from carbon based on our lines. Therefore, this formal charge is also 0, and we're all good. Last one for today. What happens when we have an actual charge on our compound? The only thing that's going to change is we need to add this electron to our valence total. So I have 5 from nitrogen, 18 from my 3 oxygen atoms, and then I need to make sure to add 1 electron just from the overall charge. And so if I add those together, I get 24. Now let's draw this out. I'm showing 3 bonds, so that will be 6 electrons, and I've got 18 left. So based on our work on the CO2 question, I know that if I just put 6 electrons around each oxygen atom, the formal charges are not going to be great, but that will be a good start just to visualize things. So I've got a formal charge of -1 on my oxygen, and I've got 3 of those, so I have a -3 charge from those. And nitrogen started with 5 electrons, but it only has 3 electrons based on the bonds or the lines, so it would have a charge of +2. And if we add these up together, we do get an overall charge of -1, which follows with the idea that NO3, or nitrate, is a polyatomic ion, and so it has a charge of -1. But the goal here is to make the electrons more accurate and to lower the formal charges as much as possible. From the CO2 question, I know that if I make a double bond here, I could remove 2 electrons from my oxygen and now have a formal charge of 0. And let's do that one more time here. So now if I do this math back here again, I now have 5 lines being represented, which would represent 10 electrons. So I've got 14 left to work with. And this has a formal charge of 0. This has a formal charge of 0. We still have a formal charge of -1 on our 3rd oxygen because I haven't given it a double bond. But nitrogen, now having 5 lines associated with it and 5 valence electrons in the beginning, has a formal charge of 0. So this is far more accurate because we're following the third rule from the previous slide, and we're also decreasing the formal charges as much as possible. If there's one thing you can take away from this, it's understanding how to use these lines in your diagrams. Because the line by itself represents 2 electrons. However, with respect to an atom or an element, it only represents 1 electron from that element that's being shared, right? So take the H2O example from before. This line represents 2 electrons, which is why we can say hydrogen is now stable, because it only needs 2 to become stable. But it has a formal charge of 0 because it came into this equation bringing 1 valence electron, and it's only sharing that 1 electron with oxygen. So that's the core difference that you need to understand between drawing the line representing your total number of valence electrons versus drawing the line and how it's going to affect the formal charge on an individual atom. Okay, that'll be it for today. Thank you for watching, and good luck with your chemistry.